that comment about swimming and cycling and running really surprises me. And I didn't know that you can find out all these things over the internet. Anyway, thank you very much to our Korea University, to the Institute, and of course to the newly formed Center for inviting me to give this talk. It's really my honor to be able to share with you what I've done in NUS. So let me start with something which is fundamental to all of us. It really brings all of us here. Resilience. So what is urban resilience? Out of all the definitions that I can find out there, I find that this particular definition may be the best, or one of the best, and that is by the 100 RC Rockefeller Foundation. And I happen to be one of the residents writing fellow under the foundation. So going with, and by this particular definition, you find that we are beginning to see the shape, the definition, the framework of urban resilience coming up very clearly. And of course, I won't have the time to go through each and every one of these items and these factors here. But I would like to say something. If you have to look at some of these factors, they are actually related to a related concept known as sustainability. So there is this ongoing discussion about sustainability on one hand and resilience on the other. And due to time constraint, I'm not going to add to that ongoing discussion. Although afterwards, I'm going to make a short personal comment about the comparison between the two. All right. And what's more, the 100 RC also define the 7 qualities of resilient cities. And some of these keywords you might have seen before, such as redundancy, robustness, flexibility, and so on. And in fact, these qualities are what that binds the research community in NUS together when it comes to resilience research. So what I'm going to show you now is just an overview of the kind of research that we are doing in NUS when it comes to different kinds of resilience. And of course, let me start with my school, since I'm the speaker. The School of Design and Environment. In SD, we have 4 main areas of resilience research. And of course, the biggest, I would say, is definitely urban planning and design. And the team behind is the team that put together and put up the annual event known as the Design for Resilience in Asia, which is a yearly design competition and seminar. And of course, we have colleagues doing construction safety, and these two are my own areas of research, which is basically what I'm going to talk about today. And of course, the Faculty of Engineering looks into resilience water supply, which is a very strategic and significant area of research for Singapore, given that we are a very small country. And of course, at the end of today's talk, I'm going to devote one slide to talk about how colleagues are now working on optimization of transportation system and infrastructure in Singapore. Faculty of Science has a very big group on biodiversity, and of course, we have the Lee Kuan Yew School of Public Policy that looks into water policy as well as different forms, different policies and as well as management method to enhance environmental preservation. So, this is what I'm going to focus on for the next few minutes, and it is this very concept of life cycle resilience. So what is that? What I've shown you here is a typical life cycle diagram in which every stage can be seen as a life cycle stage. And of course, in this case, we are talking about a life cycle of chipboard building material, which is my area. So I'm not going to talk about LCA or life cycle assessment in details. But let me give a spin to this whole picture here. What happens if we have floods, major floods, and we are going to have, or should I say we have had quite a couple of these in Singapore already, those we call flash floods. How is it going to affect the manufacturing process? It's going to affect that process if the factories are affected. How about the upstream processes or the upstream life cycle stage like this? In the forest, and access to the forest is affected, and of course all the downstream life cycle stages will be affected as well. So the research questions therefore are these. How can we assess a life cycle system vulnerability to such external shocks? And how can the vulnerability be reduced, and of course the resilience be increased? So guided by these questions, we went on to look for a framework or model to see how we can do these two jobs better. So the content of my presentation today is going to start with, as I mentioned just now, a very short discussion on the concepts of resilience and sustainability. So are they good or are they not good to each other? Well, it depends, right? These two concepts may coexist, and of course it may conflict. And these are just two examples. If we are going to make use of redundancy in everything that we build, we are going to run into some problems of sustainability. So this is just one of the trade-offs that we talk about whenever we are into sustainability research. Common roots do happen and do exist, and of course social stability, which is what I pointed out to you just now, is just one of the many examples. So if we are setting off to look for a framework to talk about life cycle resilience, life cycle sustainability is a good place to start. And by that, we have to look at some of the existing LCSA or life cycle sustainability assessment framework we have. So today I'm just going to very concisely present two of these. And I'm going to start with this one, which is basically an LCSA framework that combines all the different LCAs of environmental impact, of costing, and social LCA. Not too long ago, a few colleagues of mine from the International Society for Industrial Ecology came out with this different framework. So basically what they have done is that they have taken the conventional ISO way of doing LCA, they identify this, and they modify this into this. So if you were to allow me to blow this up so that you can see what's inside, it is this massive flowchart. So to summarize, what they are trying to say is that when we are doing life cycle studies, we have to basically broaden the object of analysis. So it's not just on the product level anymore, but it's all the way up to the economy level. That's when you can see even more trade-offs and interlinkages. Furthermore, at every level, they encourage us to look at all the three aspects or domains of sustainability: economics, social, and of course environmental effects. So by that they mean we have to broaden the scope of indicators. So is that the most perfect framework out there? Well, not quite. What I mean by that is that although they have identified stakeholder engagement as a key, as well as uncertainty analysis, you find that these are still the missing pieces. We need more wisdom and input in these areas. And there are more. So these are the 4 points that I've identified when it comes to pinpointing on the missing pieces of these existing framework. And the first point over here is definitely on the very concept of resilience and vulnerability and how they can be applied to a life cycle system. So with that knowledge and the fact that there are 4 gaps in the current framework, and these are the 4, we have come up with a new model, and some of us call it the framework known as LICSWA, or Life Cycle Sustainability Unified Analysis. Long word, that's why we need an acronym. In Singapore, we love acronyms. Everything is short form. Yong Sik will know. Will come and join us for the second time in December. Alright, so I'm a Singaporean, so I'm going to use acronym LICSWA. And of course, in this list, we find that something which is not very common, which we have considered within this framework, and that is rebound effect. And I'm going to talk very briefly about what rebound effect is about. So, okay, this is going to scare you off, but anyway, I'm going to keep this very brief. Alright, in looking for a new model, we need to look for theoretical underpinnings. So this underpinning is basically described with this in mind. And this is a measure of resilience, which basically measure how much a certain sustainability indicator, this guy, changes with time. So I'm going to basically make use of the simplest approach. That is that this term is going to be affected by a string of different factors in a linear way. That means there's no square, there's no power of 3, nothing. This is the simplest way, and let's see what we can get out of this model. Alright? So there are 3 terms on the right, and I keep this fast and short so that I can keep your attention. The first term on the right basically describes the rebound effect. Second term, the interdependence among the different life cycle stages. True enough, if you have a life cycle with 3 stages, and if out of the 3, 2 are resilient, but 1 is not, then you can be sure that all the other 2 are going to be held back by the third one. So that's the meaning of this particular term right here. And last but not the least, we have a term that will buffer the impact. So this is a good term because it will reduce the changes of that particular shock on the system. And of course, rebound effect. So many papers have been written on rebound, so I'm not going to go through this. So I'm going to summarize these 3 points with one very short sentence. Too much of a good thing can be bad. Sound philosophical, but basically rebound says that the more efficient you are in the use of natural resources can actually encourage us to use more of those resources. So we factor that into the model, and what have we got? Well, before that, there's this existing way of describing what vulnerability is about. And this is not my own creation, it's adopted by from a group of authors. What I like about this is that it brings a few things into view, and one of which is this delta, which is basically tipping point. We talked about tipping point before, and to most of us, when we do climate change research, we talk about a tipping point as being a temperature. It's more than that. If you are talking about sustainability tipping point, we really need to look for, provided they exist, the different tipping point in the economic sphere and even in the social sphere. So what are they? You have to find out. The second thing I like about this particular way of describing is that it links this particular quality, which is what I've defined, with vulnerability. And basically what that means is that the more vulnerable a life cycle system is, the higher will be the changes caused by a certain shock. And what's more, you can still retain what I've mentioned to you just now, that this factor contains the different factors we've considered, including the rebound effect, dependency among the different life cycle stages, and so on. And all these, for the first time, are linked to this term called the vulnerability of the life cycle system. Okay, can it be used? Yes, we have shown how it can be used, and I'm going to over here make use of a case study of wood plastic composite to show how this particular framework can be used. And bearing in mind, once again, that I'm not saying that this is the only way of creating this model and framework out there. There are many different ways, I believe, but ours may be the first life cycle resilience model out there. So, wood plastic composite is a kind of material that combines plastic, most of which recycled, and recycled wood fiber to make different components like this. It is quite an effective way of using recycled materials. So the background of the problem statement are these, that we assume that there is a policy being made, and the success of this policy is on the number of local residents who are engaged and who really devote their time to doing waste sorting behavior. Right? And all these are just the way we set up the model. And most importantly, a shock, a flash flood is introduced in the system. So how does the wood plastic composite life cycle system react to this shock, and what can we do about that? We went on to define the rebound effect, and I have to say that this rebound effect is not a real effect. So we are just trying to see how this system will react should there be such a rebound effect. And of course, we have defined this mathematically in our model. So what have we got? So before that, more details about how we have defined the interdependencies of life cycle stages and the stage resilience. And once again, this is what I've shown you just now. By interlinkage and of course by the dependence, what I mean is that this particular life cycle stage, for example, is dependent on how much you can access and get from the forest, and so on and so forth. And in this case study, you'll find that all these mathematical terms, suddenly they hold physical meaning. For example, this particular term means production efficiency, and that is how much you have recovered is actually used to produce the WTC, and so on. And the resilience of each life cycle stage, these terms are given this particular form. This may sound and look scary, but they are not. In fact, this is the kind of equation that you get for describing this popular curve that shows how a system rebounds or how a system recovers after a shock. So when we put all these together, this is what we get. Right, let me explain to you, and it's not going to take too much time. In the first case, the base case scenario, we find out how a system will recover over time after a shock is introduced to the system. So by right, we should be able to see the impact reducing in time. But if we consider the interactions among the stages, we'll find that there are such fluctuations over time. What happens if we are going to improve something about a system, like improving or increasing the resilience of each life cycle stage? In particular, the reduction stage, you'll find that I managed to iron out this, and the transition down is much smoother now. And what happens if the policies have been too successful, talking about trade-offs, right, or unintended consequences? What we found is that sometimes when a policy is so ingrained, so successful, that in this case, it really depends on our ability to sort our ways. When it comes to flash floods, I think the last thing in mind will be to waste or to sort our ways. And if that happens, you find that the whole system runs into havoc, and it takes a longer time to recover. So too much of a good thing may not be good after all. That's a lesson that we learned. Last but not the least, what happens if we are going to have a larger rebound effect? If we have larger rebound effect, you find that, well, that reduction is going to slow down even more. So I published this not too long ago in the Industrial Ecology Journal. And of course, this kind of idea about how individual life cycle stage resilience can help us to focus on the different types of research is helpful, and I would say that this is what that pushes us, the university as a whole, to look at the different types of resilience research. And my other area of research is of course into resource resilience construction, and that brings me to the other part of my research, which I intend to just very briefly go through. And it is about how we can make use of biochar to enhance a certain aspect of concrete, which is the self-healing aspect. Right. And, we know that when concrete ages, crack will form, and of course water will seep through, and that can cause a lot of problems like swelling. And of course, this will be a major problem if we are talking about underground construction. And in case you are thinking of just replacing cracked cement with new one, it's not going to come cheap, and not to mention that it may not be even effective. So what we have come up with is a combination of different materials and substances, like using fibers, using bacteria, and bacteria is kept, or I would like to say housed, in biochar, and of course SAP, or super absorbent polymer, which is a term that I think most of you are very familiar with. And with proper mix, we are able to make the sealing of cracks much better. And for those of you who are not really into biochar, it is just a way for us to recycle biomass. So instead of letting it decompose and return the carbon back into the environment, what we have done here is basically make use of pyrolysis to produce biochar as one of its byproducts. And then make use of that in this research house the bacteria. And this is what we talk about here. And the biochar is made at specific temperature. And of course, these are the main results that I'd like to share with you. On your left-hand side, you have a crack in normal concrete. And on the right-hand side, how or what will happen if you allow the bacteria to work. And on your extreme right, you have an SEM picture of the crystals formed by the bacteria. So since when we set off, we want to address the water infusion problem. How can we be so sure that this bacterial self healing concrete is able to solve that problem? Well, we did the kind of test that show us how this is possible. So we make use of different combination of a mixture, and we find that when we have self-healing concrete, the infusion of water from the bottom is drastically reduced, which means that there is substantial crack sealing that's taken place here. And this further shows us how, by using this particular combination, we can increase the rate of self-healing by increasing the sealing ratio across different range of sizes of the cracks. And of course, very quickly, this is what you get when you have control, and this is what you get for the green one when you make use of a combination of biochar, bacteria, SAP, and polypropylene. And this basically also shows you how that combination can give you the best effect when it comes to healing and recovery of the percussive strength. So this is a research done by one of my colleagues from another department on system engineering, in which he made use of optimization model to see how we can reduce the overall impact of any disruption in our train system, which has become quite notorious in Singapore on residents and commuters. And I'm not too sure whether I have time for this. This is one of the latest projects which I finished with the help of my two assistants. Basically, it's a combination of architectural design, research, as well as the use of life cycle assessment. And when we set off, we basically think of how we can reduce the overall impact caused by renovation of building, and to be exact, school buildings in Singapore. So over here, the third example of school C, we find has got the highest impact. So what do we do about that? We come up with a new method of design and construction, and that is that instead of tearing down and building back up again, we basically identify certain blocks, in this case the E block, where we can extend upwards in order to accommodate for more space. But to do that, we have to rearrange the space as described over here. So what we have done further is to quantify the life cycle benefits of this in terms of the cost saved as well as the CO2 reduction possible. Besides that, we also design into this whole fabric space where we can open up to allow the community to use. And by that, we define a certain index known as the generosity index. And of course, this is the last bit. Well, this is a map of Singapore. So it basically shows you where we are, as well as where the most of the population is. And if you have to look at this, you find that the darkened area is the highest area, or some of the highest area in Singapore. Singapore is quite a flat country. So the darkened area are basically areas above 5 meters. So if you are to superimpose these two slides that I've shown you, you'll find that most of the schools actually happen to be there, right in the center here. So the good news is that we can make use of school, provided that we redesign the space as center for people to go to as shelters in case there are massive floods all across the country. So in a nutshell, we feel that by designing schools within this network, we can help to reduce life cycle impact as well as to increase the generosity index. And of course, that can be used as spaces for emergencies or shelters. In other words, adaptive, flexible design can lead to better life cycle sustainability and resilience at the same time. So in conclusion, I feel that there should be much more effort on how the resilience of the life cycle of a product or service should be given more attention. And of course, second point is what I've shared with you, and that in the university, in our university, there are many ongoing research on resilience. So if any one of you are interested to know more, feel free to come talk to me. So thank you very much, and acknowledgement to our funding agency. All right, thank you for.
I guess we can take just one quick question or comment. Yes, please.
Yeah, thank you, Young Wei, for your fantastic presentation.
Thank you very much.
I enjoyed it very much. My name is Jörg Linkleber. I'm from Germany. I have just one quick question. When you were talking about your wood plastic composite, and if you are looking on life cycle, then what are you doing when the product which you produce is not used anymore? You create another problem, for instance, microplastics. You cannot burn those products. What about this point?
Okay, on the downstream process of wood plastic composite, I would say that now the option, sad to say, the option is not so much. So we either break it down and then recycle what has been recycled before. And I think that is that can't go on forever, especially now we are talking about upcycling rather than downcycling. It's not an easy question, especially if you have to bring that question to the industry. In fact, now almost all of our research, we can't even start using the plant unless we firstly engage the industry, secondly involve a certain government agency in the research. So the Singapore government has made it the norm before you can even make use of any funding from there. So I would say that the best way to address that is to really bring it down to the industry to see whether they are open to the idea of recycling of WPC into new WPC. So I do not know the answer yet. That might be possible.
All right. Thank you, Professor.
Thank you very much.